Today we're going to go through the revision quiz, see some answers here, some worked solutions, in case you got stuck or you just want to verify that what you wrote down was indeed the correct answer. Okay, now before we start, there is an equation at the top here which is a little new to us, all right, but it is reasonably straightforward to us to use. Okay, it actually comes from the one on the right hand side. Okay, the new equation is this one here. N lambda equals d sine theta. Okay, that's this one here. This is quite new to us, and that's okay. All it is that sine theta, where theta is the angle from the center line to the fringe that you're interested in. Okay, theta equals angle from middle to fringe. Okay, whichever fringe that you're quite interested in. All right, but we don't need that for the first question, so we'll not worry about that for now. Okay, so our first question here, they tell us that we've got a wave approaching a gap, two gaps rather. We know the wavelength here, lambda equals 4 meters. That's important. The boat is anchored 3 meters from A and 5 meters from B. Okay, describe and explain the effect of the waves on the motion of the boat, giving the reason. Okay, so we really want to know node or antinode. Okay, that's what we're trying to figure out. Is the boat in a node or an antinode? Okay, so let's start with the shape of the waves as they pass through the gaps A and B. And we know from experience that when the waves go through these gaps here, they produce nice circular wave fronts. Okay, something like this. Out and out and out. Oops, I'm drawing it on the wrong side. We'll try and do that a little better, shall we? They go out this way. Nice, that's more improved. Okay, cool. Off to a flying start there. Okay, something rough like that. So let's make that little bullet point. Okay, thank you. Come on. Okay, so we know the waves produce circular wave fronts. Okay, through each gap. Cool. So we're just going to state that we know that when the waves go through here, they diffract and they produce circular wave fronts. This is diffraction. Good to state the name of the phenomenon. Okay, it's diffraction. Cool. Now, they give us this information up here, 3 meters from A and 5 meters from B. Okay, that's the boat's position. So, what's the path difference? The path difference is simply one subtracted by the other. So the path difference equals 5 minus 3 equals 2 meters. The wave from B travels 2 meters more than from A. Okay, cool. So that's cool. Now, how do we relate the path difference to wavelength? And conveniently, they gave us the wavelength is actually 4 meters. Okay. Wavelength equals 4 meters. Therefore, the path difference equals 0.5 lambda. And what do we know happens when we're at half of a wavelength path difference? We know we get what kind of interference? We get destructive interference. Okay, therefore, destructive interference because we are at a node 180 degrees out of phase. Okay, that's our wave like this plus our wave like this. Okay, they're identical but 100 degrees out of phase equals, and we know that equals a straight line. Okay, so what can we say about the motion of the water at the boat? We've got destructive interference. We're at a node 180 degrees out of phase, which means the water will be calm. Calm water. Okay. If you gave a point up here, this is an achieved. If you gave a second point, this one down here, you get a merit. And if you gave the third point, indicating it will be calm, that's worth up to an excellence. Okay, very good. Let's move on and think about number 2 down here. Okay, we've got a laser. Okay, it's a laser because it's got to be coherent, the same amplitude, same wavelength, same phase relationship. Okay, and it's coming through a double split. 2 splits, very narrow, in a barrier. Okay, they've given us the wavelength of the laser. That's really nice of them. Okay, this is our wavelength here, and we know D over here are the slit spacing. Slit spacing. And we can see that that's really small. Okay, times 10 to the negative 6 meters. Really, really, really small. Okay, so down here we'll do number 2A. That's a weird way to write that. We'll try that again. 2A. Yeah, right, that's better. Cool. They want us to calculate the angle between the second bright fringe and the central bright fringe. Okay, so they want to know, this is 0, 1, and 2. Okay, 0, 1, and 2. Remembering our bright fringe in the middle is numbered 0. So they want you to, if there's a line here and a line out to here, they want to know what this theta is. Okay, and because we're projecting it onto a surface, this here, even though it doesn't really look like it, stop it, is a right angle. Okay, so if we were to look straight down, we've got our source coming out, we've got our barrier, we've got n equals 1, equals 0, equals 1, and up here n equals 2. Okay, so here's our triangle. Okay, we're trying to find this angle here. Here's our source. Okay, our slits are over there. Okay, so this is where we actually use the equation they gave us at the top up there, n lambda equals d sine theta. Okay, so we want to know theta equals our unknown. We've got lambda equals 6.33 times 10 to the negative 7 meters. We've got d equals 3.5 times 10 to the negative 6 meters. And we know we're looking for the second bright fringe. Okay, so we know n equals 2. So let's write our equation. N lambda equals d sine of theta. Okay, do we know n? Yes. Do we know lambda? Yes. Do we know d? Yes. And there's our theta, the thing that we are looking for. So let's work this out, shall we? 2 times wavelength, 6.33 times 10 to the negative 7 equals 3.5 times 10 to the negative 6 sine of theta. Okay, sine theta equals 2 times 6.33 times 10 to the negative 7 all divided by 3.5 times 10 to the negative 6. Theta equals inverse sine of all of that. Okay, and we should hopefully get an answer of 21.2 degrees. Okay, cool. So that's A done. Let's have a think about B, parts 1 and 2. Okay. How's this angle going to change if a shorter wavelength of light is used? Okay, so let's give our equation and use our equation to help us understand. M lambda equals d sine of theta. Okay. So n lambda over d equals sine theta. That will help us understand a little clearer, I think. Okay, so this first question here is asking us, what happens if a shorter wavelength? Okay, so this means if lambda decreases, the numerator is smaller, therefore the angle does what? Also gets smaller. Okay, therefore, whoops, I didn't really write my words there. Therefore, this theta decreases also. Okay. And the little thing we'll note here is that we are assuming that we don't change the other values. Okay, so we're assuming D is constant for that part there. Okay, and if we look at C, just put a line there, C, n lambda over D equals sine theta. Okay, and they're asking us to consider the situation where a slit with a smaller slit separation is used. Okay, start considering if D decreases, okay, if we reduce the separation between the two slits, what's going to happen to the angle? So that in that case, the denominator, oops, decreases. Therefore, what happens to theta? If we're dividing by a smaller number, the right-hand side is going to increase. Theta increases. And what are we assuming? We have to assume in this case that we are keeping the wavelength the same. Okay, assuming is constant. Okay, if we're changing more than one thing at a time, it becomes really hard to derive these conclusions. So we have to be assuming that we're only changing one thing at a time. Okay. If you gave me one bullet point with full explanation or working, that's an achieved. If you gave me 2 bullet points with full explanation or working, that's a merit. And 3 bullet points with full explanation and working is worth up to an excellence. Okay, very good. I hope that helps.